Hello everybody, this is Dr. Bricker. I just wanted to do a quick little tutorial about getting the velocity from a position versus time graph. So this is just some made-up data. Don't use this data. This is for the projectile motion lab. So I just made a column with time and y position. Of course you'll have an x position graph also, but this is just to illustrate how to get the velocity. That's why I just have those couple of columns. So time, position, got the units there and the variable. So I've graphed the y position versus time. And really this is a parabola. But what I want to show you is how to use the position versus time graph to get the velocities. So I'm going to put a line on this. So I'm clicking up here, curve fit, and linear. And of course it doesn't go through most of the points. What I want to do is get the velocity around just a few points. So for example, at 1 second, I want to know the velocity at 1 second. So I want to get the line that includes the point right before 1 second and right after 1 second. So let me do that and it will make more sense. So I want to deselect some of these points that are going into making this line. So to do this, I'm just hovering over it and clicking on it. And you can see there's an X through it now, and the line has changed. Same thing here, click on it. And you can see it goes away. I have a laptop here, so I'm just clicking the pad. Okay, I want to deselect everything except for the first 3 points. Okay, so then I can put the, I can read the velocity from this. So this line just includes these 3 points. So at 1 second, the velocity is the slope of the position versus time graph. So at 1 second, the velocity is 85 centimeters per second, right? This is in slope-intercept form. So the A here, the 85, is the slope. So 85 centimeters per second at 1 second. So I could take that and start building my velocity versus time graph. So I'll just call this one time, seconds, variable t. I'll call this one y, velocity. Of course, you're going to do this for the x direction as well. Velocity, centimeters per second. I'll just call it vy. Okay, so let's see, it was 1 second, right? That's the middle one here. 85 centimeters per second. Okay, 85. And now let me go to the next point. So I got to get rid of this one, but include the one right after it. So I've deselected that point, and then I've reselected this one just by clicking on it. Okay, so then at 1.1 second, this is the slope around that point. So 1.1 seconds, it's 70. So I can come down here, 1.1, 70, and just keep going through this. We'll do a few more here. Deselect this one, select the one right after it. So now this is the velocity at 1.2 seconds. And it's 55. Right, that's what the A is there, 55. Okay, 1.2. And we can keep going here. Deselect this one, select the one in front of it. So we're always having 3 points, and we're getting the velocity at this one. That's sort of the slope of the tangent line there. Okay, so 1.3 seconds, we have 40. You can kind of start to see the trend here, right? By that I mean this is going down by 15 every time. 1.4 seconds. Let's see what we have. Deselect this one. Click that one. Okay, so at 1.4 seconds, we have 25. And I'm going to have to add some more row. So let's see, insert row below, Insert row below while I'm at it. I think I have one more. Okay, 1.5, 1.6. While I'm at it, I might as well fill out this table. And then I can go back up here, deselect this one, reselect that one, and I can read this from here. That's 10, not surprising. Same thing, deselect, reselect. Okay, now you can see the slope is going to be negative. That just means we are on our way back down. -5. Actually, put the negative sign. Okay, get rid of the one before, select the one after, and we have -20. And I think we can do one more. Insert row below. Okay, 1.8. Come back up here, deselect the previous one, do that. So you're going to have, you're not going to have a velocity for the very first time because you need the coordinate afterwards, and you're not going to have a velocity for the very last time coordinate that you have. So 1.8 seconds, -35. -35. Okay, now I can make this velocity versus time graph. And again, I'm just doing the y, you'll have the x also. So over here, I'm going to put the y velocity. And then the horizontal axis, oops, done. Horizontal axis, the time. Okay, done. Okay, excellent. So this is velocity versus time. Nice and linear. That just means the acceleration in the y direction is constant. Let's put a line on this, right? This is actually a line. Curve fits. Linear. Done. Okay, so looks really good. Here's the slope, right? This is in slope-intercept form. That's the slope, -150 centimeters per second per second. That is the y acceleration, -150 centimeters per second squared. Okay, then you can come back to the position versus time graph, and we actually know that this one is from what you see there, it looks like a parabola, so I can change this back to parabola. Quadratic. And then you'll have to reselect the points here. So I'm just clicking on my mouse pad here. Okay. Excellent. So that's the way to get the velocity versus time from the position versus time graph. Let me just add one thing. I've got a couple of questions about this number 6. When on a ramp, the acceleration of gravity has been diluted to a magnitude less than 9.8 meters per second squared, or 980 centimeters per second squared, if you want to put it in the centimeters. So in class, you found on a ramp, the acceleration is g sine theta. So remember the way that this is actually made, the board is tilted, and you're looking down on this experiment. So if you're not clear about that, go back to the description of the experiment way up here. So the video shows slow motion, low friction air table, which has allows the puck to slide on the surface with very low friction. The camera is placed on the ceiling looking straight down, but the table is tilted. So this is not a free fall situation. You only have some part of gravity. So from class, on a ramp, you saw that the acceleration is g sine theta. So this acceleration here, you get from your graph. Mine was 150, the magnitude of it. G is 980. These are both in centimeters per second squared. So then you can find the sine of theta because you know A and you know G, and then you can find theta. So when it says use the vertical velocity graph to determine the angle, the vertical velocity graph, that's where you get the acceleration from. G is 980 centimeters per second squared. and then you can get that angle that way. Okay, hopefully this was helpful. If you have any questions, just email me, and talk to you soon.